Okay, let's talk about large language models. I mean, they're doing genuinely incredible things, right?
Absolutely. Writing code, summarizing huge documents, even just chatting in a way that feels surprisingly human.
But the really big ones, the most powerful ones, you pretty much need a giant server humming away somewhere in the cloud.
Right, which means you need that constant connection. You're sending data out.
Mm-hmm.
It can get costly, too.
Exactly. So the question is, how do we get that amazing power, but bring it, down to earth, onto the devices we actually use every day, your phone, your laptop, maybe even smart gadgets, without needing a server farm or constant Wi-Fi?
Yeah, that's probably the key practical challenge right now,
Uh-huh.
like making this advanced AI truly personal and accessible. And that's exactly what we're digging into today.
Okay.
We've got this really fascinating technical report on something called MiniCPM4. It's a new language model, and it's specifically built to be super efficient on what they call inside devices.
Inside devices. So AI designed to actually live on your device. So we're cracking open this paper, this report, to figure out how they did it. Our mission here, really, is to unpack the clever tricks, the innovations that let MiniCPM4 be powerful and efficient at the same time. Think of this as your shortcut to understanding how they're making these AI giants fit onto your hardware.
Okay, so let's set the scene first. We need to get our heads around the challenge itself. Like you said, today's best LLMs are enormous, just huge.
Right.
And that size means they need massive amounts of computing power, which is why they nearly always live in these big remote cloud data centers.
Which means every time you ask it something or want it to read a document, that data has to travel over the internet, which isn't great if you're offline or if you're worried about privacy or just impatient.
Exactly. And the trend here is super clear. There's this huge growing demand for models that are much, much smaller, much more efficient, so they can actually run locally.
On your phone, your PC, embedded in stuff.
Yeah. And it's not just about saving cloud costs, so that's part of it. It unlocks totally new ways to use AI, things that just aren't practical if you need that constant high-speed connection back to the cloud.
And MiniCPM4 is aimed squarely at this problem, built specifically for the kinds of chips you find in consumer gear. And they definitely grab your attention early on with some big performance numbers.
They really do. So they show their MiniCPM4 8B model getting performance that's comparable to other well-known models like Qwen 3 8B. But here's the kicker.
Okay.
It apparently used only about 22% of the training data.
Wow, okay. Less data to train, potentially cheaper to build then.
That's the idea. Lower training cost, faster iteration maybe.
But okay, less data is one thing. What about actually running it? Does it run fast on, normal hardware?
Well, this is where it gets really interesting for that on-device dream. They show a 7-fold speed improvement.
7 times.
7 times. When processing really long documents, they tested with 128,000 token contexts on an inside device. Specifically, a Jetson AGX ORAN.
Which isn't a cloud server, that's like an embedded system board, right? For robotics or edge computing.
Exactly. It's powerful for its size, but it's definitely edge hardware. Getting a 7x speed up on processing huge amounts of text locally, that's potentially a game changer for practical uses.
Okay, how do they actually do that? You don't just get that kind of efficiency boost on a smaller device by accident. It feels like they must have tackled this from a few different angles.
Oh, absolutely. It's very systematic. You can kind of break it down into innovations across, let's say, 4 key areas. The model's architecture itself, the data it learns from, the algorithms they use to train it, and then the software systems that actually run it on the hardware.
Makes sense, like optimizing the engine, the fuel, the manufacturing process, and the driver.
Huh. Yeah, something like that. Let's start with the architecture, the foundation, specifically how they handle those really long texts efficiently, because that's always been a major hurdle.
Right, the standard way models pay attention to all the previous words gets really slow with long documents, doesn't it?
Precisely. That standard self-attention mechanism, it's brilliant, but the amount of computation and memory it needs grows quadratically with the text length.
So double the text length, 4 times the work.
Roughly, yeah. You can kind of brute force that in the cloud if you have enough power, but on a device with limited memory, limited processing, it just falls over when the text gets too long.
Ouch. Okay, so their fix changes how the model pays attention.
Yes. They use something called trainable sparse attention. It's part of their InfLLM v2 architecture. The core idea is, look, instead of calculating attention between every single word and every other word in a huge document, which is incredibly expensive,
Yeah.
The model learns to be selective. It learns to focus its attention only on the most relevant bits of the past text to predict the next word.
Kind of like how we skim read a long report and only really focus on the important sections.
That's a really good analogy.
Yeah.
And the model learns what's important during its training. The way it works is pretty clever. It doesn't just look at individual words or tokens in the past. It groups them into blocks, and it uses what they call semantic kernels. You can think of these as little summaries or representations of what's in each block without needing to process every single token in that block, just to figure out if the whole block might be relevant.
Ah, so it's judging chunks based on a summary, not word by word. Saves work.
Exactly. Then, for the current word it's trying to predict, it dynamically picks out the top K, the few most relevant blocks, based on how well their semantic kernels match the current query, the current context.
Makes sense.
And they also build in a rule. Always include the very beginning of the document, and always include the words immediately before the current one. Because, the intro often sets the scene, and what was just said is usually critical.
Totally. Don't forget the beginning or what you just said 5 seconds ago. Basic conversation rules.
Right. And here's another neat optimization. They structure the model, so different parts of the attention mechanism, different query heads, looking for different kinds of relationships, can actually share the same set of selected relevant blocks if they're in the same group.
Ah, so they don't all have to fetch the same data independently.
Exactly. Cuts down significantly on memory access, which, as we said, is a major bottleneck on edge hardware. And this whole architecture is designed to speed up both parts of the process, reading the initial long prompt and generating the response word by word.
And this architectural change is what helps tame that costly quadratic scaling. Gets it down to something more manageable.
That's the goal. By only paying attention to a limited number of blocks, the core computation complexity drops from being O squared, quadratic in length L, to something much closer to O, linear, for the critical part. They give details on kernel sizes and strides, but the big picture is this architecture makes long context processing actually feasible on constrained hardware.
Okay, smart architecture deals with the model structure. But, any LLM is only as good as its training data. Are they just using a smaller chunk of the same giant web scrape everyone else uses?
No, not at all. And that's the second key innovation area, training data. Their philosophy seems to be very much quality over quantity. They know that just grabbing everything off the web gives you massive scale, sure, but it's also full of junk, repetition, low-quality stuff. So if you want high performance from a smaller model trained on less data overall, that data has got to be exceptionally good.
Junk meaning irrelevant text, weird formatting, just not very informative.
Yeah, all of that. So they put a lot of effort into cleaning and curating their data. For the initial pre-training data, they developed something called UltraClean. Now, a big challenge when you're cleaning data is knowing if your cleaning process actually helps the final LLM learn better.
How do you test that without training a whole new model?
Exactly. Training a full model from scratch just to test a batch of clean data is incredibly slow and expensive. It's like baking a whole wedding cake just to see if the flour's okay.
Okay.
So their efficient verification strategy is clever. They take a model that's already nearly trained, and they just incorporate the new candidate data during the final stages of its training. This gives them much faster feedback on data quality without that huge upfront cost.
Smart shortcut.
And then for the actual filtering, deciding what data to keep or discard, they used a classifier based on fast text.
Fast text, isn't that like a much simpler model compared to a full LLM? Why not use a powerful LLM to filter?
Cost and speed. LLMs are computationally heavy. Using an LLM to filter trillions of tokens would take forever and cost a fortune. Fast text is way, way faster and cheaper to run, especially on CPUs. They processed 15 trillion tokens for cleaning using fast text in under 1,000 hours. They estimate doing the same job with an LLM-based filter would have taken over 6,000 hours on GPUs.
Whoa. That's a massive efficiency gain just in cleaning the data itself. That's often overlooked.
Absolutely. Cleaning the data efficiently is a huge part of the puzzle. Then for the next stage, supervised fine-tuning, that's where you teach the model to follow instructions and have conversations. They created UltraChat v2. And this isn't just grabbing random chat logs from the internet. It's specifically focused on generating high-quality, complex dialogue data. They used other expert models and very careful prompt engineering to create conversations designed to teach deep reasoning, handle back-and-forth interactions well, and tackle complex tasks.
So they're not just imitating existing chats, they're actively creating teaching examples for the harder stuff.
That's exactly it. The aim is to create text that's well-formed, logically coherent, sometimes structured like examples you'd find in a textbook, or really detailed form discussion.
Yeah.
The idea is to instill knowledge and reasoning patterns that you don't find densely packed in typical web data. It's curated quality trying to build specific skills.
Okay, got it. Smart architecture, super high quality data. What about the training process itself? Dimension 3, any special tricks there?
Yep. Training algorithms, optimizing how the model actually learns. They use a few techniques here to make the training itself more efficient. They briefly mentioned something called ModelTunnel V2. Yeah, it sounds like a system they use to experiment with different training strategies on smaller models first. Find out what works best cheaply before scaling it up to the bigger, more expensive models.
Like testing the recipe on a small batch before you cook for a crowd. Makes sense.
Exactly. Then there's something called chunk-wise rollout. This is specifically for optimizing the reinforcement learning phase.
RL, okay. That's often used to teach more complex behaviors, right? Like reasoning.
Right. But standard RL rollout, where the model generates long sequences, can apparently lead to inefficient GPU use. Like some GPUs might be working hard while others are just waiting. Chunk-wise rollout processes the outputs in fixed-size chunks, which helps keep all the GPUs busy more consistently. It reduces wasted computation during that specific, often tricky training phase.
Okay, so optimizing the training workflow itself. But you mentioned efficiency.
Yeah.
What about making the model really tiny, like pushing the boundaries of smallness?
Yes. That brings us to CPM4. This is their approach for extremely low-bit models. And this is absolutely key if you want to get genuinely powerful AI onto devices with very, very limited resources.
Low bit, you mean quantization, making the numbers inside the model simpler.
Exactly. Model quantization. Reducing the numerical precision of the model's parameters, its weights. Instead of using, say, 16-bit floating point numbers, you might use 8-bit or 4-bit integers. This drastically cuts down the memory needed to store the model and often speeds up the calculations during inference.
Okay, 4-bit is pretty small. Does CPM4 go even further?
It does. They explore ternary LLMs. Ternary meaning the weights are quantized down to just 3 possible values, meaning 1, 0, or 1.
Whoa, -1, 0, or 1. That's it. Instead of thousands or millions of possibilities, that's
Yeah.
incredibly low precision.
It's extremely low. And when you go that low, just taking a normally trained model and squashing the weights down afterwards. Post-training quantization, or PTQ, usually tanks the performance. You lose way too much accuracy.
So you have to train it differently. Train it knowing it's going to end up with only those 3 values. Quantization-aware training, QAT.
Exactly right, QAT. But training a ternary model like this from scratch is known to be really hard and needs enormous amounts of data. So their approach is an efficient 2-stage QAT.
You're right.
They start with a pre-trained, high-precision MiniCPM4 Model 1 that already works well. Then they fine-tune that model with the quantization awareness, teaching it to work well with only 1, 0, and 1 weights.
So starting from a model that's already smart gives them a massive head start for that final, tricky QAT phase.
Precisely. And this turns out to be a huge efficiency win. They claim their CPM4 needed only about 10% of the data tokens that another ternary model, BitNet2B, used to reach strong performance, thanks to starting with the pre-trained model.
That's clever. Leverage the initial training.
Yeah. And the results look pretty compelling. Their CPM4 1B model performed competitively with other 2 billion parameter models. So similar power from a much smaller ternary footprint.
Impressive.
Though they do note their smaller 0.5B version struggled a bit more with really hard math or coding tasks, which, you know, is a good reminder that even with all these clever tricks, raw model size still counts for something, especially for complex reasoning.
Makes sense. You can only cram so much knowledge into a tiny box, even if it's a very cleverly packed box. Okay, so architecture, data, training algorithms, including that super low-bit version. What's the final piece? How do they actually get this running fast on all the different kinds of devices out there?
Right, that's the fourth dimension, inference systems and deployment. Because having an efficient model is only half the battle. You also need the software stack on the device to run it efficiently.
And that's tough, right? Devices have limited compute, memory, power, and the hardware landscape is kind of a mess. NVIDIA, Qualcomm, MediaTek, Apple, everyone's got their own thing.
It's a huge challenge. Fragmentation is a major headache. So first, for NVIDIA GPUs specifically, they developed their own lightweight CUDA inference framework. They call it CPM.cu. It uses standard optimization techniques like static memory management, figuring out memory needs up front to avoid slowdowns later, and kernel fusion, which combines multiple small computing steps into bigger, faster ones. And importantly, efficient speculative sampling.
Speculative sampling? That's where a smaller draft model guesses the next few words, and the bigger main model just checks the guess, right? Speeds things up.
Exactly. And their specific improvement here is called FR-spec, frequency-ranked speculative sampling.
Okay, what's the frequency ranked part?
So the potential bottleneck in standard speculative sampling can be the output layer of that small draft model, especially if the main model has a huge vocabulary, tens of thousands of possible words.
Right.
FR-spec says, look, in any language, a small number of words are used way more often than others. The A is and, etc. So let's restrict the draft model so it only predicts from a small subset of these most frequent tokens.
Ah. So the fast guesser only needs to worry about the most common words.
Precisely. The main model still uses the full vocabulary when it verifies the guess, so you don't actually lose the ability to generate rarer words. But the draft model, which runs much more often, becomes dramatically faster because its output calculation is much, much simpler. They estimate this reduces the draft model's head complexity by up to 4 times.
That's a really neat trick for inference speed. Okay, what about getting those quantized models, like the 4-bit or the ternary ones, working well on device? Any specific optimizations there?
Yes, that leads to PGPTQ, prefix-aware post-training quantization.
Okay, break that down. Post-training quantization.
That's when you take a fully trained model and then quantize it afterwards. To do that well, you need to run some sample data through the original model to figure out the best way to map the high-precision values to the low-precision ones. It's called calibration.
Got it.
What they found is that the activation patterns, the internal numbers for the very first few tokens in any sequence, tend to be outliers. They behave differently compared to the tokens that come later in the text.
Huh. So the start of the document kind of messes up the calibration for the rest of it.
Pretty much. So PGPTQ, the prefix-aware part, is simple. It just excludes those first few prefix tokens when calculating the statistics needed for quantization. Don't let the weird start mess up the average.
Simple but effective, sounds like.
Yeah. And their specific method, called SPGPTQ, apparently showed the smallest drop in performance compared to the original high-precision model in their tests. They point to Table 4 in the paper for that.
Okay, so they've optimized the core inference and the quantization for devices, but what about that hardware mess you mentioned? Different chips, different software libraries.
Right. That's where ArkInfer comes in. This is their cross-platform deployment system. It's designed to be a unified way to run MiniCPM4 and potentially other models too across that fragmented hardware landscape.
How does it do that? Magic.
Oh, not quite magic. It uses an abstraction layer. Think of it like a universal adapter. Underneath this layer, they have specific adapters that know how to talk to different hardware backends. They list support for things like Qualcomm's NeuroPilot, MediaTek's Genie, Rockchip's RK-LLM, NVIDIA's TensorRT-LLM, even the open-source llama.cpp.
So it's like a universal remote control for LLMs that works with different brands of hardware TVs?
That's a great analogy. This layer lets the core inference system work consistently, while the adapters handle the specifics of talking to each hardware acceleration library. You don't have to rewrite everything for every chip.
Smart.
And ArkInfer also supports various useful decoding strategies on these devices, things like their accelerated speculative decoding, which they call beta, and also constrained decoding using something called guidance.
Guidance. That's for making the model output stuff in a specific format, right? Like JSON or SQL.
Exactly. Super important if you want the LLM to reliably interact with other software or tools, not just generate free-form text.
Yeah, essential for real applications.
And the whole ArkInfer system includes things like an extensible model zoo front end and an automated pipeline to convert models, making it easier for developers to actually get MiniCPM4 up and running on lots of different target devices. It's really a comprehensive approach to tackle that deployment challenge.
Wow. It really sounds like they've thought through the entire pipeline, hasn't it? From the fundamental math inside the model, the data, the training, all the way down to the nitty-gritty software that makes it run fast on your actual phone or whatever. It's not just one single trick.
That's exactly the takeaway. No single silver bullet here. It's the combination, the synergy of innovations in architecture, data, algorithms, and the deployment systems all working together. That's what unlocks this kind of efficient performance. And they didn't just build the tech, they show it working with some concrete applications.
Okay, tell us about those. What can you actually do with this kind of on-device power?
Well, they highlight a couple of interesting examples. One is MiniCPM4 survey. This is a version based on the 8B model that's specifically designed to generate trustworthy survey papers, like literature reviews in science or tech.
Okay.
The huge advantage of having this run on your device is privacy. If you're dealing with confidential research data or sensitive company documents, you probably can't or don't want to upload all that to a third-party cloud service just to get a summary written.
Absolutely. That's often a non-starter.
Running it locally keeps your data completely private. And it's also way cheaper. Generating long, detailed survey papers involves processing and generating a lot of text, which can get really expensive with cloud models that charge per token.
Yeah, those costs add up fast. So how does it work?
They describe a plan retrieve write process.
Huh.
The model first plans the structure of the survey, then it retrieves relevant information, presumably from local files or databases you give it access to, and then it writes the actual survey content.
And how good is it?
Pretty good, apparently. Their evaluation showed its content quality was comparable to systems using much larger models, like GPT-4o. And interestingly, they found it was even better on factual accuracy in their specific tests. Table 7 in the paper shows this.
Wait, running locally, smaller model, but more factually accurate than a system using GPT-4o.
In their tests, yes. That's a pretty significant claim. It shows that this focus on efficiency doesn't necessarily mean sacrificing capability. It might even offer advantages in some areas like factual grounding, perhaps due to the focused data or architecture.
That's really impressive. Okay, what was the other application?
The other one is MiniCPM4 MCP. This version is designed to reliably use external tools, things like calling a calculator, searching a database, querying an API using a standardized protocol they call the Model Context Protocol, or MCP.
Okay, why is that important? Don't LLMs already use tools?
They do, but often in a very messy, ad hoc, non-standardized way, which makes building reliable applications that integrate LLMs with other systems quite brittle. Using a defined protocol like MCP aims to make that tool interaction much cleaner, more robust, more predictable.
Makes sense. Standardization helps.
And their evaluation, shown in Table 8, indicated that MiniCPM4 MCP actually performed better than the larger Qwen38B on their tool use tests. Why? Because their model was specifically fine-tuned using demonstrations of interacting with tools via this MCP protocol. It learned the language of the tools better.
So again, not just running locally, but potentially being better at practical tasks like reliably using external systems because of how it was trained and designed.
Exactly. It really highlights the potential for these efficient on-device models in real-world applications, if you look at their overall evaluation results summarized in the paper.
Yeah, give us a quick summary.
Okay. The MiniCPM4.5b model is competitive with other models around the 1 billion parameter mark. The MiniCPM4.8b model holds its own against models up in the 10 billion parameter range. They show particularly strong results on Chinese language benchmarks.
And the long context.
Handles it well up to 128,000 tokens, and that sparse attention keeps things efficient, using only about 5% sparsity in their tests. And then the headline efficiency numbers. Those significant speedups on edge hardware like the Jetson AGX Orin and even on desktop GPUs like an RTX 4090. Especially noticeable as the context gets longer, hitting that up to 7x decoding speedup compared to Qwen38B on the Jetson is a really strong proof point for on-device performance.
Okay, let's pull back again. Connect this to the bigger picture.
Right.
What's the fundamental takeaway here? What's changed?
I think the fundamental shift is this. MiniCPM4 provides really strong evidence that powerful language understanding and generation are no longer exclusively tied to giant cloud data centers. It shows a concrete, viable path to bring that kind of sophisticated AI capability right onto the devices you already own. It manages to combine genuinely strong performance with remarkable efficiency, and it does it through this systematic innovation across the board: architecture, data, training, deployment. It's a big step towards making advanced AI feel less like a remote service and more like a ubiquitous personal tool that's just there.
And they release the models and code too, right?
Yes, which is huge for the community. It allows others to build on this work, experiment, and accelerate progress in making AI truly efficient and accessible.
So let's bring this home. What does all this mean for you listening to this deep dive right now?
Well, it means the whole world of possible AI applications could be about to get a lot bigger and a lot more personal. Imagine AI that's not just in the cloud, but running right there on your device, instantly available, handling your data completely privately, helping you write, code, analyze information, interact with the world, even when you're offline.
So here's the thought to leave you with. Given that models like this MiniCPM4 are pushing efficiency so hard, running on quite limited hardware, even down to those incredibly simple ternary weights, and they're designed to be deployed across pretty much any chip out there, what kind of totally new applications or maybe just widespread accessibility could truly powerful, efficient, on-device AI unlock for you in the near future? What might you build or what problems could you finally solve if a capable LLM was just there on your device, always ready?
Definitely something to think about as this technology continues to race forward.